What is a convolutional neural network and how does it work? Let's start with the basics. A convolutional neural network represents a class of neural networks that excels in processing image data. These networks are commonly seen in applications where a computer needs to identify objects in pictures, though they're also quite effective in natural language processing tasks. The fact that they are useful for these fast-growing areas is one of the main reasons they're so important in deep learning and artificial intelligence today. Once you understand how a convolutional neural network works and what makes it unique from other neural networks, you can see why they're so effective for processing and classifying images. But let's first take a regular neural network. Such a network comprises an input layer, several hidden layers, and an output layer. The input layer receives various forms of data, the hidden layers compute these inputs, and the output layer presents the results of these computations and analyses. Each layer contains neurons linked to neurons in the preceding layer, and each neuron is assigned its own weight. This setup does not presume anything about the incoming data, which is generally beneficial but not ideal for dealing with images or text. Convolutional neural networks approach data as having spatial relationships. Instead of every neuron being connected to all neurons in the preceding layer, connections exist only among nearby neurons, all sharing the same weight. This architectural tweak maintains the spatial integrity of the data, ensuring that, for instance, the network doesn't misconstrue an eye to be scattered across an image. The term convolutional pertains to the network's filtering process. Imagine an image as a complex entity. A convolutional neural network simplifies it, enhancing the processability and comprehension of the image. Let's explore the components of a convolutional neural network. Similar to a standard neural network, it consists of multiple layers. Unique layers like the convolutional layer and the pooling layer set it apart. Focusing on the convolutional layer, it functions by overlaying a filter onto an image pixel array, generating what's known as a convolved feature map. This process resembles peering through a lens, highlighting specific image features that might otherwise remain unnoticed. Following this is the pooling layer, which condenses the size of the feature map, thereby streamlining processing by reducing the computational load. Yet it also includes a ReLU or rectified linear unit layer for activation and a fully connected layer for classification. The ReLU layer introduces nonlinearity, preserving the essential dimensionality as data traverses the network. Without this layer, the intricate details we aim to capture would diminish. The fully connected layer, on the other hand, facilitates data classification. For those interested in exploring CNNs in a coding environment, you might want to check out tutorials or playlists dedicated to deep learning, such as those by Mike Harris. It's hoped that this overview has enriched your understanding of convolutional neural networks, highlighting how their convolutional layers, equipped with powerful filters, form the backbone of their pattern detection prowess. If you found this explanation enlightening, consider engaging with more content through likes, subscribes, and comments. Thank you for watching, and stay tuned for more insights into the fascinating world of neural networks.